This is a Lorenz Attractor. It's a type of strange attractor with a distinct butterfly-wing shape, and it's become one of the most recognizable parts of a branch of mathematics known as chaos theory. So, firstly, what is a strange attractor? Well, we know from David O'Reilly's paper on the subject that they consist of infinitely many points that correspond to the states of a chaotic system. These points are stretched apart and later rejoin the system in smaller regions. This means that 2 points that are close at one point in time might be wildly far apart later on, making it almost impossible to predict exactly where the system will be on the attractor. There are also, in many cases, fractals, which is just the term for geometric shapes that are self-similar across different scales. The Lorenz system from which the attractor can be graphed is a set of equations in which x is equal to sigma times y minus x, y is equal to x times rho minus c minus y, and z is equal to xy minus beta c, where sigma is equal to 10, beta is equal to 8/3, and rho is equal to 28. It is particularly useful in weather prediction models due to its ability to demonstrate how weather might change between two regimes. In Tim Palmer's paper, A Weather Eye on Unpredictability, he describes it as two different wings representing a zonal and a blocked regime. 2 points representing nearly identical states of weather, arbitrarily close to one another on the left-hand wing, which shows a zonal regime, could evolve in 3 different ways. They could remain on the left-hand wing, they could shift to the right-hand wing, or they could split between the 2 different wings. Now, alone, it would only be able to give us a vague sense of the weather forecast due to its simplicity, so the Lorenz Attractor must be used alongside other observations about initial atmospheric conditions. It should also be kept in mind that there isn't really a set number of times a certain trajectory has to circle around either wing. It's still an unpredictable system. So, if you're like me and you want to experiment with the Lorenz Attractor, Goethe University Frankfurt offers a simulation created by PhD student Henrik Wernick. Here you can adjust rho, which acts as a parameter, to graph different versions of the Lorenz Attractor. It should be noted that while the graph seems to show different parts of the butterfly crossing, this isn't actually the case. No part of the attractor can ever cross back over itself, as you can see in these graphs.